Welcome back, everyone. This is section 4.3, back to our probabilities. And today we're going to learn about the multiplication rule and independence. So let's define what we mean by independence. Two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E affects the probability of event F occurring. We have two examples here. So our first example is speeding on a freeway and then being pulled over by the police. Are these independent? No. These are dependent. You have pancakes for breakfast. This is example 2. You have pancakes for breakfast and your best friend gets an A on her exam. Those are independent events. They have nothing to do with each other. And we all have superstitions, right? Hopefully we know not to take too much stock in those. So if we want to know what the probability of event E and F occurring, assuming that they are independent, we multiply the probabilities together. This doesn't seem very complicated, but as you'll see, it's going to get a little complicated. And let's start with our first example. At a local college, 61 of the male students are smokers and 549 are non-smokers. By the way, I want to point out this means that the number of males, total are 61 plus the 549, which is 610. Of the female students, 78 were smokers and 522 are non-smokers. So once again, the female total is going to be the 78 plus the 522, which ends up being exactly 600. This is important because this is going to be our denominators here. A male student and a female student from a college are randomly selected for a survey. What is the probability that both are non-smokers? All right, so we have one male and one female. So what's the probability of both are non-smokers? Well, there are 549 male non-smokers out of a total of 610. And for the female, there are 522 out of a total of 600 females. So we need to multiply those together. The way I'm going to show how to multiply this is not the only way. There certainly is more than one way to do this. I like grouping the numerators together. 549 times 522 divided by 610 times 600. And I'm getting 0.783. Not too bad. Of the people who fished at Clearwater Park today, 45 had a fishing license and 45 did not. Of the people who fished at Mountain Valley View Park today, 90 had a license and 10 did not. And no one was at both. Suppose the one fisher from each park is chosen at random. Find the probability that the fisher from Clearwater had a license and the fisher chosen from Mountain View did not have a license. Let's start out here. I'm going to use CW to represent Clearwater. And the total at Clearwater is the 45 plus the 45. Total of 90 people went fishing at Clearwater, and the Mountain View, there was 90 plus the 10, which is 100. Again, those are my denominators here. So we want to know the probability that Clearwater has a license and Mountain View does not. So how many at Clearwater has a fishing license? That's 45 out of their 90. And how many in Mountain View do not? Looks like 10 did not out of the 100. Let's see what we get. And that drops quite a bit. And there we are. All right, moving on. A news organization surveyed 70 adults. Each said he or she gets news from only one source. And here's a summary of the sources of news: television, radio, newspaper, and internet. I'm sure those numbers are different today, but part A says, oh, there's not a part A, sorry. The question says 3 of the adults in the survey are selected at random, one at a time without replacement. Now that is important to know, that there's no replacement. Meaning once one is chosen, they are removed from being eligible of being chosen again. What is the probability that all 3 of the adults get news from the newspaper? Ooh, let's see. This is all newspaper. I haven't read a newspaper in a very long time. All right. First of all, they tell us that there are 70 total. That's going to start out as my numerator or my denominator. And there's 14 I can choose out of the 70. But once that first person is removed from the pool, there's now only 13 that read the newspaper out of the remaining 69. And then once those 2 are chosen, there's only 12 that read the newspaper out of the 68. So notice it's dropping down by 1 each time because we are not replacing. So let's see what we get. Yep. And let's see what we get. It's about 0. I want 3 decimal places. That's fine. 0, 0, 7. That's what that's going to round to. Next up. Suppose 2 cards are randomly selected from a standard deck of 52 cards. Part A. What is the probability that the first card is a club and the second card is a club if the sampling is done without replacement? So again, once we've removed a card, that card is not put back into the deck for part A. So the probability without replace. And, oh, sorry about that. Without replacement. So how many clubs are there? There are 13 clubs out of the 52 cards. But once we've taken one out, there's only 12 left out of the 51 cards. This is where the no replacement comes in. That there. So let's see what we get here. (13 times 12 divided by 52 times 51. I'm getting 0. They don't say where to round this one off. 0.588, I'll say. And let's take a look at part B. Part B is the same question, but with replacement. So in other words, once we pull a card out and it's a club, we put it back, shuffle the deck, and then pull it again. So this is the probability with replace. Well, that's going to be 13 out of the 52. Again, once we put the card back in, there are now 13 clubs left in there, again, out of the 52. So this is actually 13 out of 52 squared. you can see the probability is a little bit higher than our previous answer. Which stands to reason there's more cards and there's more possibilities of getting a club if there's more clubs in the deck. All right, for our next example here. Due to a manufacturing error, 8 cans of regular soda were accidentally filled with diet soda and placed in a 24-pack. Suppose 2 cans are randomly selected from the 24-pack. I want to make it clear, first of all, that this means that there are, in this 24-pack, there are 8 diet and 16 regular in this 24-pack. Part A. Determine the probability that both contain diet soda. Now, we're assuming once we take one out, it gets drunk and we throw it away, so we're not going to replace it. So we're assuming all of these are not replaced. Both are diet. So that means that that's going to be 8 out of the 24. Now that we've taken it out, that's going to be times. There's only 7 left out of the 23 remaining. Let's see what we get. I'm getting a little over 10% chance of that happening. 1, 0, 1, 4. Could happen, wouldn't be too weird. Or B. What's the probability that they are both regular? Well, there are 16 regular to start out of the 24. And after we've taken that out and drank it, there are only 15 left out of the remaining 23. And this is definitely higher. As expected, there are more regulars in there anyway. Not too bad. All right, we're going to add a layer to this. We're going to talk about at least probabilities. And for that, we are going to use the complement rule. And you can see below where I just highlighted, it says the probability of at least one individual having a property is equal to 1 minus no individuals having a certain property. All right, so let's go to our example. Among 30 to 35-year-olds, 38% say they have danced in public while under the influence of alcohol. Suppose 5 30 to 35-year-olds are selected at random. Now, here's how this goes. So there's 5 people from this group that are selected. It's possible none of them have danced in public while under the influence. It's possible one of them has. It's possible 2 of them have, or 3 of them have, or 4 of the 5 have. It's possible all 5 of them have done this. We have all these different possibilities, and it gets quite complicated. So for part A, it says, what is the probability that none of them have danced in public while under the influence? So just to be clear, 38% have. That means 1 minus 0.38, 62% have not. All right, so part A says, what is the probability that none of them have? Well, that is going to be 0.62 times 0.62 times 0.625 times. We end up here. Zero 0.62 raised to the 5th power. By the way, my the way I get to the exponent on your and how you would do it on your calculator, mine is right above my division button. It's a caret. It looks like it's a symbol that looks like this on a button, and that's the exponent button. Your calculator may have a different button, so you'll have to find it for yours. And here we are. So this is about 0.0916 is what I'm getting for that. So each of these 5 people that have not, there's a 62% chance that they, for each individual one, that they did not dance while under the influence. And when there's 5 of them, and we're assuming that none, and we're selecting only ones that have not, you can see that drops just a little above 9% probability of that happening. So part B says, what is the probability of at least one? There we are. At least one has danced in public. That means it needs to be, what's the probability of exactly one of them, plus the probability of exactly 2 of them, plus the probability of exactly 3 of them, and so on. So the easier way to do this is to use our complement rule. So the probability of at least one is going to be the same as 1 minus the probability that none of them have. I'm going to go 1 minus, and I'm going to use the answer button, which is right above my negative button down at the bottom there. It's blue on mine, so I have to hit the blue button first, and then I hit the answer button down below. And what that will do is that will use the previous answer, the 0.0916 and so on up there, so I can get all those digits. So we end up with 9.908. I'll just stop there. So that goes up to 90%. 90% probability that at least one of these randomly 5 selected people have danced in public while intoxicated. On alcohol, specifically. Part C, what is the probability all 5 have danced in public while under the influence? Okay. So that is just this one here. Only looking at that, just all 5 of them have. Well, that is going to be, each one has a 38% chance, and that's all 5. So that's 0.38 raised to the 5th power. 0.38 raised to the 5th power. Very low probability of this, 0.0079. And there we are. Not too bad. We just have to really think about it. And you're going to want to look for that at least in some of your homework problems as we do this. Let's do another one. Christmas lights are often designed in a series circuit. This means that when one light burns out, the entire string of lights go black. Suppose that the lights are designed so that the probability a bulb will last 2 years is 0.995. The success or failure of a bulb is independent of the success or failure of the other bulbs. Okay. So, part A says, what is the probability that in a string of 100 lights, all 100 will last 2 years? So this is the same as the probability none break. Not break, stop working. Meaning they're all working. Well, that's going to be the 0.995 for each light bulb. So that's 0.995 times 0.995 times 0.995, exactly 100 times. So let's see what we get. Look how far down that dropped. Went down to just a little above 60%. So 0.995 looks really good, but when we have 100 of them, and each one has its own probability of 0.995, then that drops quite a bit. Part B. Probability at least one. Well, that's going to be the complement of 1 minus the probability of none break. So 1 minus 0.60577. And I'm going to use my little trick on my calculator again. I'm going to use the previous answer here. I'm going to go 1 minus. And again, I'm using the ANS button down at the bottom, right above my negative button, right next to the enter button down at the bottom. Mine is blue, so I have to push the blue button first, and then the answer. And that's going to go 1 minus the previous answer. There we are. All right. That's our at least scenario. Let's move on to our conditional. The notation, the P with the F, the bar, and the E is where the probability of event E given, the probability of event F given event E. And I'm going to tend to use this formula, so I'm going to use the numbers instead of the probabilities. It ends up being the same thing. So this is saying, what's the probability of F happening, assuming that E is going to happen? Well, we take however many fit into both categories and divide that by the number in E. It's too confusing with letters like that. Let's actually jump on this. 8 balls are numbered 1 through 8, are placed in a bag. Some are gray and some are white. Hopefully that's coming through. It looks like 2, 6, and 8 are gray. The rest of them are white. Answer the following and write your answer as a fraction. We will see that it does not matter if we write in a reduced fraction or we do actually reduce it. It will not matter, especially in ALEKS. Either answer is fine. So a ball is randomly selected. And let me explicitly write out. So there are 3 gray, and they spell it with the E, the English way. And that makes there 5 white. All right. Part A. What is the probability that the selected ball is white? Okay, that's easy. That's going to be the 5 out of a total of 8. That's it. It's no problem. However, part B is a little bit different. It says, what is the probability that the selected ball is white given that the selected number is less than 7? So this is saying, find the probability that it's white given that it's a number less than 7. Well, if we write out the numbers, 1, 2, 3, 4, 5, 6, 7, 8, how many are less than 7? There are 6 numbers less than 7. And that's the given. So that is our new denominator. And how many of them less than 7 are white? Well, I'm going to circle. I see 1, 2, 3, 4 of them. And this is where you can reduce it if you want or not. I'm just going to leave it as is. All right, let us move on. All right, Dr. Hayes is a veterinarian who sees only dogs and cats. In each appointment, she may or may not give the animal a vaccine. The two-way frequency table summarizes Dr. Hayes's 70 appointments last week. Now, what I like to do real quick is I like to write down the totals. So 7 plus 18 is 25. 21 plus 24 is 45. The total number of dogs is 28. So that's the 7 plus the 21. Total number of cats, that's the 18 plus 24 is 42. This may or may not come in handy. We'll see. All right, part A. What is the probability of randomly selecting a dog? Okay, how many dogs are there total? There's 28. So it did come in handy this time. This is out of the total of 70. Right, that was given to us up here, 70. Or you can add everything up, of course. And they want the answer as a decimal. So 28 divided by 70. About a 40% chance that we will be selecting a dog if we randomly select one of these. This was part A. Part B. The probability no vaccine and a dog. So we're looking at both. So no vaccine and it's a dog. Well, again, my denominator is 70. No vaccinated dogs, I'm seeing that there's only 21. And I'm going to choose, oh, we need to do a decimal. 21 divided by 70. It's only about a 30% chance of randomly selecting a dog or a cat out of the dogs and cats, a dog that has not been vaccinated. There. And now we're to that given clause, part C. What's the probability no vaccination given that it's a dog? So probability no vac given that we're only choosing out of the dogs. That means my denominator needs to be the dogs only. How many dogs are there total? There's 28. And how many non-vaccinated dogs are there? 21. Again, that's the same pink highlight there. So about a 75% chance that we will get a non-vaccinated dog, given that we're only choosing from the dogs, meaning for part C, cats are out. They're not part of the equation at all. That's why the denominator is not 70 for that one. All right, we're almost there. Once again, I'm going to add these up real quick for us. Number of parents is, even before I even read the problem, I'm going to add this up as 118. Total number of children is 35. Total number of pencils, whatever that means so far, we don't know. Total number of cups, 62. Total number of magnets is 50. You don't have to do this. I'd like having that information in case it does come up. Local parents and their children were invited to the grand opening of a daycare center. Each of the 153, that's the total, attendees got to spin a wheel and win a prize. The table below summarizes the data on the attendees and the prizes. So just make sure we're reading this correctly. There were 8 children that won a cup as a prize. And there were 37 parents that won a magnet for a prize, and so on. Suppose an attendee from the grand opening is chosen at random. Answer each part and do not round your final answers to the nearest hundredth. So we're getting a decimal for this one. Okay, here we go. Part 1, what is the probability that the attendee is a parent and won a pencil? Probability parent and pencil. All right, so the denominator is going to be the 153. And how many parents were there that won a pencil? Let's see, I'm seeing 27. So there is my numerator. So let's see what we get. 27 divided by 153. And they said round up to the nearest hundredth, 0.1, and that'll go to 8. Part B, what is the probability that the attendee is a child or won a magnet? Ooh, okay, so we're back to our addition rule. This is from the previous section, but we can do this. Probability child or magnet. Well, that's going to be the probability of randomly selecting a child plus the probability of randomly selecting a magnet minus the overlap. Probability of choosing a child and a magnet. Okay, so let's start with probability of a child. How many children are there total? It looks like there are 35 out of the 153. Probability of winning a magnet. So how many magnets were won total? That is the 50 out of the 153. And then I have to subtract off the overlap, which is the children that won a magnet. How many children won a magnet? That looks like 13 to me. Let's add up those numerators. 35 plus 50 minus 13. 72 out of the 153. Let's see what we get. I'm getting about 47% probability of that. All right, so that was a kickback to the previous section. And our last problem of the day. A group of 220, actually, before I even read that, I'm going to total these up real quick. Improvements, 55 plus 66 is 121. 77 and 22 is 99. Old medication, 55 and 77 is 132. And 66 plus 22 is 88. Again, I may not even use some of this information, but we'll see. A group of 220 patients tested a new medication. Some tried the new medication and the rest took the old medication. The results are reported in the following table. The patient is chosen at random from this group. Complete the following, write your answer as decimals. They do not say how to round it off, so maybe that won't be necessary. Part A, find the probability that the patient showed improvement. So this is just overall improvement. So total improvement, I'm seeing the 121 out of the 220. I'm getting that 220 number from right here. They totaled that for me already. So let's see what we're getting. 121 divided by 220. Oh, okay, so this rounds off nicely for us. All right, so about a 55% chance of that happening. Part B. Find the probability that the patient showed improvement, given that he took the new medication. Okay, so that means that I need, the numerator is going to be the people that improved with the new medication. So let's see, new medication and improved, that looks like 66 to me. I'm getting that from here. And the denominator is going to be everyone who took the new medication. So how many people took the new medication? That looks like 88. So 66 over 88. I'm getting 75. All right, and let us interpret this. Is there evidence that a patient who takes the new medication is more likely to show improvement than a randomly chosen person from the group? I'm going to say yeah, 55% to 75%. That's a pretty darn good jump. So let's see. The first one says yes, because probability found in part B is much greater. Yeah, so that sounds exactly right. And that is section 4.3. I hope that was helpful.